Today, Theorems for Free is by Lars Hupel, who works for INNOQ, and he is one of the founders of the Title Initiative. But he will tell you more himself.
Yes, thank you. It's been a while since I've given a Haskell related talk, so I'm obviously very excited. The topic of Theorems for Free is very dear to my heart because I did my PhD in the field of logic and verification, and I've proved theorems for a living. I got paid for proving things. So obviously, I'm very excited about theorems. And interesting enough, I've given a Java flavored version of this talk at various Java conferences because I was trying to tell people that generics in Java are not evil and you should be using them more. And at MuniHac, of course, the audience is a lot better for this because you all already know that type parameters are good and that you should use parametric functions. So in this version of this talk, I'm going to focus a lot more on the underlying mathematics that is behind the Theorems for Free concept. And but of course, I will also explain what this means. And I think you're in luck that you're in this talk because I will just freely give out theorems for everyone. So I have theorems for everyone. There's an unlimited supply of theorems. You can get as many theorems as you like. I'm not sure if the other speakers in the other slots do that. So what is this talk about? This talk is about a concept that has been introduced by these two people. So the first person here is John Reynolds. John Reynolds is a computer scientist. Both of them on this slide are computer scientists. So John Reynolds has introduced a concept that's called parametricity. And then Philip Wadler later came along and packaged this up quite nicely and written the paper Theorem for Free. And this is exactly what the talk is also called. Both of these papers are quite old. And both of them also require a bit of mathematical fluency to understand. So I will be trying my very best to start basically from scratch, where from scratch means you have some basic idea of how types work in Haskell. So if there's anything that's unclear or if there's any mathematics that's a little too much on the slides, please speak up on Slack. And I also have a flip chart here, so we can turn this into a full lecture if necessary. So I will be happy to explain some things on the flip chart if that's necessary. I need to switch thing, and then we can get started. Okay, so let's start with types in Haskell. So the basics that you need to know for this talk is basically just two things. The first thing is that in Haskell, type variables are lowercase, and I will try to stick to that convention here, even though sometimes I use slightly different syntax. And the second thing is that all types in Haskell are erased, which means that the runtime has no access to whatever's going on during compile time. And kind of a third point here for the talk, for the most part of this talk, is that we're going to ignore type classes for now. They can be accommodated in this calculus, but they're making things a little bit harder. So I will just try to ignore them for now, and we just assume that we have no type classes. We just have some type variables, basically. What I mean with erasing, so if you write the identity function in Haskell source code, you would write that as follows. You would say ID is of type A to A. And this is what the compiler sees, and this is what you can work with. However, what the runtime sees is more like this. It looks more like a function that takes some kind of pointer or some kind of word, some kind of machine thing, and turns it into another machine thing. And you don't really know what the A is there. In languages like Java, for example, you can use the get class, for example, to inspect what's going on. But in Haskell, basically, the idea is that all type information is lost as soon as your compilation is done. And this is seen as a good thing, right? Because the folklore says the more type variables, the merrier, right? Make your functions as generic as possible. And we kind of have an intuitive understanding why this is true, why we would want that, because the more generic a function is, the more type parameter it has, the less power it has. So the less bad things it can do, right? So a function that takes an int and returns an int can do arbitrary things with that integer. But a function that takes an a and returns an a can do nothing with that a. It can just return that a unmodified, right? So just by looking at the type signature, we can already infer a few things from what the function does. And if you're hanging around in the Haskell community, then this is basically described as sort of reasoning with types or reasoning about types. And what I want to do in this talk is I kind of want to give a more formal understanding of what that actually entails and where this is coming from. Of course, this folklore, the more type variables the merrier, can also be taken to a particular extreme. So yeah, I mean, all of you know that there's this that there's a lot of discussion in the Haskell community about length libraries, and some people prefer one over the other. And I don't want to give a value judgment here of which length representation is better. The point is here to show that it is in fact possible in Haskell to write extremely abstract type signatures, and those type signatures may have advantages for reasoning, but at the same time they may have consequences for understanding what's going on. Right. So to summarize, we want usually more type variables because then we can reason about types. But the question is, how does that work in mathematics and the underlying theory? Now, for the remainder of this talk, I will be using set theory to explain some of these concepts. If you are familiar with category theory and type theory and so on, I would like to say that many of the things I'm saying have asterisks attached because you cannot clearly map these types to sets, but it is a reasonable approximation. So please forgive me, I know very little about category theory, but I've read that all of this can also be categorically motivated if necessary. But I'm personally a big fan of set theory, so this is what I'm going to stick with for now. Right, so quick refresher. In set theory, everything is a set, well, almost everything is a set. And we can express many things that we know, like the natural numbers as a set, right? So, for example, the natural numbers is a set that starts with 0 and then just goes up. Or we could have the whole numbers, which also includes negative numbers, right? And in particular, in set theory, also functions are sets. So this is a representation, a graphical representation of a function that maps shapes to their colors. So we have a red triangle, and that is mapped to red. We have we have a red triangle, and we have a yellow rectangle, and the yellow rectangle is mapped to the color yellow. And what we intuitively understand a function is something that takes an input and sends it to some output. In set theory, this is also represented as a set. So the function f in set theory is just a set of tuples, and the tuples are inputs mapping to outputs. That's the thing. Now, of course, not all sets are functions, right? So it's only a function if it's unique. So in this example, we cannot have the red triangle being sent to two different outputs, right? So it's only a function if it's unique from input to output. And what's interesting now is that we can look at a representation of types that can be mapped to sets. So I've used some brackets here, and these brackets are sometimes called denotational brackets, because what we're doing here is we're looking at the denotation of a type. And what that means is we take a type, which is a concept from Haskell, so it's a syntactical thing, like bool. It's something that you could write in Haskell source code, and then we look at the mathematical denotation of this concept. So we're basically trying to look at this from a whole new abstraction level. So we have some kind of concrete source code that we could compile with GHC, and then we look at kind of the abstract idea that's behind these types. And this is what's called a denotation. And the denotation for Bool, for example, is just a set that contains two things, namely true and false. For integer, the denotation would be the set of all the whole numbers. So the starting from negative infinity and so on, going to plus infinity. If you already look very closely, is that I've used the integer type here and not the int type, because the int type is restricted. It only goes to what the machine allows you to do. So I've used integer here because that's more along the lines of the mathematical representation. And of course, there are already here some asterisks attached, because of course, in memory, in a machine, you cannot represent arbitrarily large numbers, because at some point you will run out of memory. But these are all things that I would like to ignore for now, and we will just look at the abstract mathematical ideas. Right. So third line here, we look at the denotation of a tuple type. So we have a tuple type that in Haskell we write with parentheses and a comma. So we have a tuple of type A and B. And what is the denotation of that? Well, the denotation is basically the Cartesian product. So Cartesian product is a set theory construction that basically means tuples, right? So we can also construct, we have tuples in Haskell, and we also have tuples in mathematics and set theory. And we can also look at the denotation of a function type, for example, and that would be just a set of all functions that send values from the denotation of A to the denotation of B. And based on this, we can basically give denotation to almost all types very easily. The question is, of course, what do we do with polymorphic types? All of these things are solvable, but looking at this requires some pretty hefty set theory, so I will not go into detail on this. Why am I telling you this? The reason is that there are many different interpretations of types. In Haskell, what we like to think is that types are something that restructure your program. So the compiler gives you an idea of what is possible to do. You give a type annotation to function, then it kind of determines what you can do with this function. But we can also look at types from different angles. So we can also look, as I said, at the mathematical abstractions behind them. And in fact, this is very important when you want to prove something like type safety, right? Just because you have a type system doesn't necessarily mean that the type system is good or it respects type safety. So if you want to do some kind of formal reasoning on your compiler, that your compiler does the right thing, you would need to look at the denotations of these types and kind of ensure that on the machine level you don't do anything wrong that could risk the type safety of the program. Now, you can also interpret the algebraic data types, like lists, for example. And what's kind of funny is that in the paper by Wadler, he uses the notation A star instead of what we in Haskell would write as A in brackets. Now, does anyone have any idea why he would be using the star? If anybody knows, you can type it in Slack. I'll give you a few seconds to think about it. Okay, I see no one typing, so I will tell you. A star, the star operator, kind of reminds you of regular expressions, hopefully. And it turns out that this is exactly the same concept. This is called the Kleene star, and the Kleene star basically is like a repetition of elements. So in denotational denotational semantics, you can consider lists to be arbitrary length sequences of things, and then you take some kind of union operator over these things, and all of this is abstracted using the Kleene star, and the Kleene star applies to many concepts in set theory and language theory and so on. So it's really versatile, and I find that kind of interesting that all of these separate worlds are somehow connected to each other. And of course, if you're into category theory, this will be all old news, because I'm pretty sure that there's a long-standing, all-encompassing definition of what the cleaning stars in category theory. But I'm the wrong person to ask about that. Okay, now that we've talked about sets, let's talk about relations. A relation is also a set, and it's kind of a generalized function. So if we want to have, if we want to take a look at how two sets A and B relate to each other, we can write that as follows. We can write it as relation R, and relation R is always a subset of pairs of A and B. So the most trivial relation would be a relation that relates nothing to each other. So you have just an empty relation, it's possible. Or you can have a relation that relates everything to everything else. Okay, that's possible. But of course, you could have some relations like, let's say A is integers and B is strings. You could have a relation that says an int is related to a string if the string has the length of the int. Right? So you could have the int 5, and it would be related to all the strings that have length 5. And as you can see, this is a generation of a function because you can have an arbitrary m-to-n mapping between those two different sets. And in Haskell, you can write a relation just as a function that returns bool, a function that takes two parameters, a and b, and returns a bool. That would just be a relation. So you can check if the two values are related to each other or not. And now the cool thing is that we can not only map types to sets, and this is the notation of types, sets that contain all the values of that type, but we can also interpret types as relations. And this is really the key thing that's been introduced in this paper by John Reynolds, that we can give a meaning to types based on relations. And that's really an interesting thing. So to summarize, we can assign every type T a relation, and we can give that relation a particular name. And I will use in these slides, I will use a subset, so like an index. So I will say it's rel T. So rel T is the relation that corresponds to the type T. And this relation will always relate values of that type to the same type. So this kind of looks funny, right? I will give my best and try to explain what the meaning of this is, right? So why are we relating values of one type to the values of the same type? And let's start out with ground types. So ground types are just very basic types, no type variables, no nothing. For ground types, these relations are identity relations. So if we look at the relation for bool, we just see that we relate true to true and false to false, right? So we don't do anything else. It's just basically like the identity function. It's nothing exciting going on. And for integers, for example, we just map 0 to 0, 1 to 1, and so on. Is that clear so far? Any questions up until this point? Okay, I see no one typing, so I'm going to go ahead. Now, things start to get more interesting if we look at more complicated types. For example, if you look at lists, because lists are types that take, so the list is a type constructor, which means list by itself is not a type, but we need some kind of type parameter, like list integer or list string or something like that. Or in general, we have lists of type A. And these relations now suddenly start becoming higher order. So just as, so types, like regular ground types have simple relations, and type constructors like lists, they have kind of higher order relations. So they take a relation and produce a new relation. So let's say we have a list of A and we have some kind of relation for this type variable A. Now we want to check if two lists, X's and Y's, which are lists of A, are related to each other. When are they related? There are two conditions. The first condition is they need to have the same length. And the second condition is they need to be pairwise related. So every item in each list needs to be related to each other. And I have an example here. So let's say our relation says that the second value needs to be double the first value, right? So we can choose an arbitrary relation because, as I said, it's a higher order relation. It takes a relation and produces a relation on lists. So if you have two empty lists, they are always related because they have the same length, but there's no elements in there to check, so they're always thought to be related. Then I have here two lists. We have 1, 2, and 2, 4, and those are also related because 2 is double of 1 and 4 is double of 2. So this makes those two related. Now, if we have two lists that have separate length, like 1, 2, and 2, 4, 6, that's not related because they have different length. And in the last item on the slides, if we have the two lists 1, 2 and 0, 1, they are also not related because they fail this double constraint. Now, this is not exactly like zipping two lists because if we zip, as in like if you use the standard library function zip, it will just take the shorter one and discard all the other elements. So this is kind of different. Don't think of this as zipping, but think of it as aligning two lists together and checking each element pairwise. Yeah, if we have this, if those two constraints are satisfied, same length and pairwise relation, then we say these two lists to be related. Okay, so let's up this one more and let's talk about how to relate functions, because of course functions have types A to B, and I told you that we can assign a relation to every type, so we can also discuss when are two functions related. And this is slightly tricky. So two functions are related when they send related inputs to related outputs. So let's say we have a function from A to B, or maybe let's make it concrete. Let's say we have two functions that send strings to integers. Maybe it's the length of the string, or some other kind of operation that it performs on these strings. And these two functions are related if when I give them two related inputs, then the output should also be related. So basically, we have two functions. We have one function here, we have one function there, and we send two inputs to these functions each, and we look at the outputs that those functions have produced. And then, if the inputs are related, then the outputs must also be related. And if this holds for every possible input that you could think of, then those functions are also related. So in general, you can always imagine this kind of like when are two functions equal somehow? Well, two functions are equal if when you give them equal inputs, they also give you equal outputs. And you need to check that for all the different inputs. This is what's called extensional equality, because you always check that on all possible inputs. And of course, in general, this is not computable. In Haskell, you could not write such a checker that checks if two functions are equal. But you can think about this from an abstract mathematical point of view, because in mathematics you can just do proofs on all different inputs. You just have to make the proof, right? Functional relation works kind of like that. You look at all the possible inputs, and if they're related, and then the outputs are related, then those two functions are also related. And we can write this down formally. So we have two functions, f and g. They have both the same type, and they're related if and only if when x and y are in the relation A, they're related to each other, then f of x and g of y also need to be related to each other. So that would be the formal way of writing this. And for everyone who's curious, can also see the exact same definitions in the papers from Reynolds and Wadler. Now, you might have one of those two reactions. So the first reaction is, I did not sign up for mathematics class. What's going on here? I don't understand anything. And the second reaction is, you have said so much about mathematics. When can we actually see the theorem for free, right? You promised you would hand out so many theorems, but so far there are no theorems yet. And this is true. All of this is the setup. So I've talked about 25 minutes. And I have about an equal amount left. And in the second half of this talk, I will actually talk about the applications of this, like what follows from this. All that you've seen so far, the interpretation of types and sets and relations are the necessary methodology in order to understand what's going to happen now. So the next thing I will talk about is actually parametricity. And just as a quick update, any questions so far? Anything I've said is unclear, or is everyone waiting for these theorems to come out of this talk? Okay. I see no questions, so I will be moving on now. So
there's one writing.
Someone's writing. Type now or be silent forever. Okay. No, I don't. Someone is typing. Okay. Thumbs up. Okay, I will be continuing. So the central theorem in this entire story is the so-called parametricity theorem, and it looks kind of simple. What it says is then if we have any Haskell term of a particular type t, so small t and big T, then this term t is related to itself according to the relation of that type. Yeah, so every term is related to itself. But yeah, what's the point of all this? Essentially, this theorem talks about these relations that we have just defined, relations and functions and so on. And by itself, the theorem itself doesn't really say much. It doesn't really look useful. But when we apply this theorem in a particular way, when we look at all of these definitions of relations, we can infer a lot of interesting things. And let me skip back a few more slides. In particular, for these relations on functions, I told you that those relations are higher order. So we can plug in arbitrary relations for the input and for the output. And this is what we're going to use now in order to prove things. So let's say we have some function on maps, right? So we have a function that takes in a list of A or returns a list. It takes in the list of A and returns a list of A. And parametricity, the parametricity theorem now states that this function is related to itself. And I used the which here because I didn't want to print out the entire relation. So there's some kind of magic going on here. And when we instantiate this somehow in a clever way, then we can prove something. And what we can prove is this. And I will give you a few seconds to understand this proof or like the statement that we can prove. Okay, so what's going on here? The proof or the theorem that we can prove basically says that when we have a list X's, and we first plug it into Frobnicate. We don't know what Frobnicate does, so we just plug into Frobnicate and hope for the best. And then we pipe that entire thing through map. So we take the result of Frobnicate and map it with another arbitrary function that we don't know. Then it's the same thing as if we had mapped first and then plugged it into Frobnicate, right? So what this says is that Frobnicate actually does not care about the values in the list. The only thing it can do is it can shuffle around the structure of this list, right? So one possible thing that Frobnicate could do, it could actually return the empty list always, right? And let's say Frobnicate returns the empty list. Let's check what this statement says. Well, if Frobnicate always returns the empty list, then on the left-hand side, we have Frobnicate of something returns the empty list, right? So that's the empty list. On the right-hand side, we first call Frobnicate. So we're getting empty list, and then we have a map on the empty list, and that's also the empty list. So that's true. Frobnicate could also do something else. It could reverse the list. And we can also check if that kind of makes sense, if it does that. So on the left-hand side, we first do a map, and then we do a reverse. And on the right-hand side, we first do a reverse, and then we do a map. And of course, both of these things are the same, right? So reverse of map and map of reverse is the same thing, because reverse doesn't care about the values in the list. It only cares about the structure and shuffles around the structure. And this is kind of a class of theorems that you get from this approach of theorem for free. It kind of tells you that because Frobnicate has nothing else than the list of A's, the only thing it can do, it can look at the structure of the list. And this entire thing follows from the fact that Frobnicate is related to itself. So we can plug in the appropriate relations and get out this kind of theorem. Now, I have a question from another channel that I will answer now. And the question is, I said that in Haskell, it's impossible to write a function that checks if two functions are equal. And the question is, can I do it in Idris? And the answer is, you can try to prove it in Idris, but it's an uncomputable thing. So in general, you cannot, it's undecidable. So you cannot write a function that always returns true or false if two functions are equal. There's actually a very interesting paper, I think it's called Seemingly Impossible Functional Programs, which explains in which case it is actually possible to decide in some special cases. But I'm not going to talk about this now, because this is like an entirely different can of worms. Okay, so far, this is what we can prove about Frobnicate. And we can prove all of these things just by looking at the type signature. And that's kind of interesting, right? We didn't actually have to look at the implementation of Frobnicate. We only had to look at the type signature. And this, of course, also explains why more type parameters are better for reasoning, because let's say the Frobnicate function doesn't talk about A's, instead it talks about strings or about integers. Then it could do a whole host more other things. It could, for example, compute the sum of all of these integers. And it could do, I don't know, like, it could do arbitrary things with these integers. It could negate them or whatever. And the theorem that comes out, the last line of the slide, wouldn't actually hold, because it only holds because we have the type parameter A going on there, and because we can exploit that the relation for Frobnicate is higher order. So we can plug in arbitrary relations and get something out. If we have as a relation list of int to list of int, all of this is fixed. We have some fixed relations, and we only have equality that we can talk about. And that's not very exciting. We can't infer anything from this. So long story short, theorems for free, we can get them from the type signatures, but they only prove something interesting if there's actually any type variables going on. Otherwise, there's nothing interesting that you can follow from the function. Okay, now what? At this point, I hope that maybe if before the talk you had no idea what you were doing when you were looking at type signatures, now you have some idea of what's going on. And of course, I do not expect anyone to be able to just look at the type signature and immediately see, looking behind the matrix, all the theorems that come out. But when I'm done with the slides, I can show you a few, I can show you a website and some other tool that can actually help you with that reasoning, so you don't have to do it by yourself. You can just type something in and get the free theorem out. To summarize, what I've told you is that function with type variables, they don't know anything about the input, and they can't do much with that. And this is kind of a consequence of the parametricity, and also that Haskell does type erasure. Right? So if in Haskell I had some way of getting hold of types that were present during compile time, then I wouldn't really be able to do that. Someone asks if this is the only theorem that we can prove about Frobnicate. No, it isn't, but it is actually the most readable one. So we can generalize this theorem a bit more, but then it would not be really readable at all. So you can generalize this to arbitrary relations, and you can talk about how Frobnikate relates to some other functions, but this is not extremely readable. So the paper by Wadler actually goes into great detail what you can actually follow, and then he kind of instantiates this to some more reasonable theorems. Right. Someone else is typing. Do we have another question? Okay, I will just give Gabo some time to type. In practice, there's some really profound things that we can also do. There's a really interesting blog post by David Kuchen. He's also around today. He's organizing this thing. And there he proved that the second functor law is actually redundant. So functors, as we think of them in Haskell, have two laws. So the first is the composition law, and the second is, the first is the identity law, and the second is the composition law. And it actually turns out that if you have proved the identity law, you get the composition law for free. So that's pretty neat. So we could basically just, we can just get away with doing some small manual proof, and then the other proof kind of falls out from that. Yeah, so there's this website, which I will show later, that's just called Free Theorems. It's by Joachim Breitner. So he uses an underlying library that's called Free Theorems. It's a package. And I don't exactly remember who wrote this library, but Joachim put this on the web and gave it a nice front end. And in there, you can just type a function signature, and you can make some configuration, and then you get some of the results back, but I will show this in the demo later. Okay, so Gabor is asking about what happens when you have constraints, like type class. I will talk about this in a moment. Right, so I will also show another free theorem about a kind of mapping function. So you have the type A goes to B, and then it takes another list of A, and then it produces a list of B. And we all recognize this as the type of the map function, the regular list map. And the free theorem for this says that this function is either map, or it is a map that also shuffles around the order of things, right? So it can't do anything else in that. This kind of is a consequence of this, what I told you about the Frobnikate function. So the Frobnikate function, for example, can also always return an empty list, and this is also what a map function could do. Like, so the function with this type could also always return the empty list, or it could reverse it or something. But the point is, it can do nothing else in that. So it can be map and then do some rearrangements, but nothing else than that. And I mean, intuitively, this is kind of clear, right? If our result list contains some B's, how is it supposed to get these B's except for if it shoves it into the A to B function, right? So, for example, if we give it an empty list as input, the only thing it can do is produce an empty list of B as an output, because it cannot conjure any B's out of thin air. It needs an A to obtain a B. And of course, all of this is kind of intuitively clear, but I hope that now you can also trust a kind of sound mathematical foundation behind this idea. Okay, so there's a few restrictions. For example, if we have endless recursion or any kind of other bottom like exceptions, it destroys all of the beauty of what I just showed you. Some things survive. Basically, there's a paper that's called Fast and Loose Reasoning is Morally Correct, which talks a little bit about this, more how we do intuitive reasoning about Haskell programs. And the good news is that not everything is destroyed. There's still a bunch of things that survive. If you want to be really sure, you can just prove for your functions that they terminate and that they do not that they're terminated, that they're productive, and that they do not throw any exceptions, and you're still golden. You can still good to go. You can still obtain the theorems. But of course, if there's any kind of non-termination going on, you will run into problems. Right. So also extensions. So far, we have ignored classes because they complicate things. But from an intuitive point of view, classes can be made part of regular type signatures, right? So we don't actually need any kind of constraints are not actually special. What they are is we can model them as dictionaries, and those dictionaries complicate some things a little because potentially we have rank 2 types or even higher rank types, if you want to model this. There's another paper which I will link to in the Slack, which talks about how to, for example, incorporate the monad type classes into these free theorems. So all of that is actually possible. The free theorems website, I think it actually supports equality constraints. So we can take a look at this now and figure out if it actually what's actually happening there. All right. I'm at this point at the end of my slides. I would like to switch to a bit of demos now. So if there's any question that involves the slides, please ask them now. And also feel free to unmute yourself if you want to. You can also just talk to me now.
Yeah, you could raise your hand in Zoom, or I can allow everything to unmute himself if that works out nicely. And a little reminder that we have a Slack channel, and you find it under join.munihac.de, and there's a link. Or you can, if you are already on the MuniHac workspace, you can search in the browser, but then I allow to unmute themselves. So if anyone has a question.
Okay, a few people are typing, so I think we have enough time even for the demo afterwards. So just go ahead and ask something. Okay, so someone asked if I could describe the parametricity theorem again, and I can certainly try to do that. Let me find the slide that states the theorem. Okay, here we go. So the parametricity theorem itself, as I said, is not very exciting at all. We have all this machinery to look at the denotation of types. So we can assign types to sets, and those sets describe what values are possible for these types. And we can also, at the same time, assign relations to these types. And those are kind of the characteristic relations that may or may not be higher order. So anytime we have some polymorphism going on, then those relations are going to be higher order. And the idea now is that if we write any term in type lambda calculus or system F or Haskell, whatever you want to call it, then we know, based on the way this is defined, based on the way these calculi work, is that if we have any kind of closed term, so anything that does not contain any free variables, anything that's that can be evaluated, then the value is related to itself. So we have this entire machinery with all the relations in the sets, and the parametricity theorem basically reaffirms that all the definitions make sense. That every term is related to itself based on these relations. And that by itself, as I said, is not extremely exciting. But by plugging in particular relations into these higher order relations, we can then infer these kind of free theorems. That makes sense. I hope I have clarified this. Next question is, does theorem for free say anything about the ST monad? And I'm pretty sure it does, because ST monad is defined just in terms of Haskell itself. There's nothing magic going on there. So to be fair, I haven't thought about what the actual results would be, but you could try plugging it into this web interface and see what happens. It supports data type definitions. So that is data types can just be assigned to relations too. So this should be possible. Okay, so Heinrich asks, what exactly is that which type? How do we instantiate this in a clever way that gives you the theorem about map? Let's put that aside. I can show that in a second demo, and I will show that at the end because it's going to get very technical. So if you're interested in seeing that, stay online and I will show you. Okay, so the question is, are rel A and rel B related in some way? And I'm assuming, let me find the slide. I'm assuming that refers to a particular slide. Jens, could you confirm this is the slide that you're meaning? Yes, okay, so this is the correct slide. And the answer is no. Those two relations are completely separate, and this is the power of parametricity, because we can plug in arbitrary relations into there. And this is the trick we're going to use. Okay, so I will now switch to the first demo. So I will end sharing my slides, and we'll start sharing my browser. So please give me a second for switching over to this. Okay, where's my browser? Where's my browser? Okay. Going to share my browser now. Where is it? Here is it. Okay, so this is the website, and I will send the link to the Slack channel. And this is just, I can just reload it. It's all client side. And you can type an arbitrary type signature here. And then you can choose a particular language, a sublanguage of Haskell. So for now, let's use no bottoms. And no bottoms means what it says. There's no general recursion and no exceptions or anything going on. And by default, if you don't specify anything, you get this free theorem. And as you can see, this is not entirely completely intuitive what's going on here, because that relates to a previous question. This is the most general thing that you can prove, or that's the most general thing that comes out from this. So you have all of these relations going on here, and this means basically we are lifting the relation R into lists. So this is the relation on lists. And then we can make some simplifications here. We can, for example, click the type, hide the type instantiations and so on, and then just look at the bottom here, and then we see, well, this is the actual theorem that is this is the actual equational theorem that we get, and this is also kind of a permutation going on here. So we have map of G applied to F is the same as F applied to map. So it doesn't matter if we first apply map or if you first apply F, it's the same thing. Now we can try, so this is a kind of a filter function, I guess. We can try making this a little more complicated by adding, for example, a general recursion and selective strictness. And then we get this precondition, this additional precondition, and we say that this P and this Q that we apply here, they must not be bottom. Otherwise, it doesn't work. Let's try as another thing. If we can add some constraints here. So maybe let's try a function that kind of looks like a sorting function or something like that. Let's use EQ. I haven't tried this out, so this is, let's see what happens. And let's go back to no bottoms here. And what do we get? We get the same result. So we also get this map in F. Switching around, but we get some additional constraints. So we need to know that this G function that we plug in there, it needs to respect equality. So basically what it says is G needs to be a function even if you consider arbitrary equality relations. And you know, I understand that this may be a little hard to parse. So this is why I tried to exclude classes for most of the part of this talk. But just basically to answer the question, yes, it is possible to include classes. If you have constraints in your types, then your theorems will become a little bit more complicated, but you can still prove things about it. Okay, we have another question. Are free theorems with type variables always naturality squares from category theory? I don't even know what naturality squares are. I'm not sure if anyone in the call that understands category theory, because I don't. So yeah, please discuss this offline, because I have no clue. All right. So I think this concludes all I wanted to say. So I will switch over to the second demo now that is going to become extremely technical. I will show a tool that's called Isabelle. And in preparation of this talk, I have prepared a few of the proofs from this talk. So if you're interested in seeing this, please feel free to stick around. Let me find that window. Okay, share screen, and we have Isabelle. Okay, so what is Isabelle? Isabelle is a proof assistant. So if you've heard of Coq or of Idris or of Agda, Isabelle is kind of like that. It uses a completely different theory below the others. Sorry, it uses a different theory underneath than what the other proof assistants use. So it's basically set theory. And the interesting thing about Isabelle is that in Isabelle, the parametricity theorem doesn't hold in general. So in Idris and other of these systems, you basically always have parametricity because it's based on type lambda calculus. And Isabelle doesn't have that. But the nice thing is that you can reason about parametricity quite easily, which is not as easy, for example, in Agda. And we can define functions here. For example, we have a function that it's like the identity function. It just takes an A and returns an A. And we can assume that this function is parametric. So this is just some piece of code that says this function is related to itself. So we have the function relation and its f is related to f. Okay, so now we can prove that f and g can be switched around. So we have the same commutativity theorem here. And let me open the proof state. So I understand this is a little hard to read, but someone asked for it, so I'm going to show it. What we can do is the following thing. Let me try to type this again so that it becomes a little bit more obvious. So f is here now the parametricity theorem. So this says that f is related to f. And the question mark a here at this point means that we can instantiate this with an arbitrary relation. We can just put anything in there that we want to. And first of all, I'm going to unfold the definition of what the relation of function means. So we first unfold this definition and we see, well, this is the definition I've showed on the slides. So if we have two x's, if we have an x and a y, and they are related, then the outputs also need to be related. And this rule format thing is just a bit of busy work that we need in Isabelle to make it a little bit more easy to use. And now we can actually instantiate this relation with the following relation. So the relation that we use is we say x and y are related if y is the output of g of x. So basically, we just stick the function g in there. That's all we do. We stick the function g in there because functions are a special case of relations. And then we get this theorem. So we say if y is equal to g of x, then f of y is equal to g of f of x, right? And you can already see that this kind of looks similar to the thing that we actually want to prove. So we can instantiate x with x and y with y, and then we get this result. And the same thing we can do with functions on lists. So this is the propagate function that just takes an arbitrary list and returns another list. And it is also related to itself. And here we have this rel fun operator. And we also have a relation on lists, which for historic reasons is not called rel list in Isabelle, but it's called list all two. And we can do the exact same trick here. So I can also develop this again. So we can unfold the definition of this thing. Then we get this. So we need two x and y's that are related to each other. Then do some busy work. And then we can do the exact same instantiation. So we also use this xy, y is equal to g of x. I will paste that. And then there's another theorem that we need to use. So this is a theorem that I have proved above. And this theorem basically talks about turning one of these relations back into a function. So it's kind of an unlift of this. So we can unfold this and then do some more busy work that's going on here. And we have this, and so we have a similar assumption or similar thing to that we can use for the proof as above. So there's just this map that's going on here, and if we compare this with above, it looks basically the same, just that there's a map, additionally a map going on here. Right. So someone said instantiate y with g of x. Yeah, that's true. I think I said this wrong. So we can also be a little bit more explicit about the instantiation if we want to. We can say where f is equal to this. Nope, that's wrong. What's the variable called? A, sorry, where a is equal to this. And x is equal to x. And y is equal to g of x. So yeah, that's true. Right, and then we can see directly that we can prove this. Right, and we could also be a little bit more. Careful with instantiation here, but Isabel has kind of powerful automation. So in general, you would try to avoid instantiating these things and let the automation do most of the things. But yeah, so this quick digression just serves to show that you can actually do these reasoning in a formal setting, and there are proof assistants that allow you to do that sort of thing. Okay, right. I hope I didn't scare anyone off from using free reasoning, but in any case, I am available in Slack and happy to answer any follow-up questions that you may have, or you can also just hit me up on Twitter if there's anything else on your mind. Otherwise, yeah, I think I'm done with all the content. Thanks for sticking around, and yeah, see you around at MuniHac.
Thank you very much. A little applause, please. You can unmute yourself or write applause in the Slack chat.
Thank you.
Do we still have questions? Anybody?
I see Johannes typing in the Slack channel. I think he knows a thing or two about category theory, so feel free to bother him with categorical questions. Yeah, so Johannes asks about more examples of free theorem which I would use. I will defer that to the paper by Philip Wadler. There's a lot of mathematical content there, of course, but there's also a few theorems that he outlined and proved there. I'm going to link all of these resources that I mentioned here in the Slack channel and for follow-up reading.